Good afternoon, everybody. And first of all, I would like to thank the organizers for inviting me to present in this symposium. And I would like to apologize for not being able to be with you in person. I will present our work on machine learning for optical network security management, which we have been doing at Chalmers in Sweden. But this work is also a result of collaboration with our colleagues at Telecom Italia, MIT, Infosim, and Chalmers, whose role I would like to acknowledge here. Today in my talk, I will first introduce you to the optical network security landscape. I will then present our machine learning framework to diagnose physical layer attacks, and I will present our experimental results and performance analysis. As we are all aware of, it's extremely important to have a high degree of security in communication networks. This has been emphasized by many different bodies, and a recent example is the statement from the Internet Governance Forum, where they coined the need for Internet of Trust. Basically, they recognize the true digital revolution as the greatest single enabler of sustainable development, and emphasize the lack of trust and security in cyberspace as potentially detrimental on all the opportunities that this evolution brings forth. The lack of trust and security in cyberspace can come from many different layers, domains, devices, and network infrastructure is no exception to this. In the recent survey from Microsoft, the vast majority of businesses identified cyber attacks and cyber threats as their biggest concern. While digging deeper into the sources of these concerns, a Cisco report ranked network infrastructure very high with this respect. Management of optical network security is a challenging topic due to several different factors. I will try to list some of them here. The fiber plant is deployed outside of a secured perimeter, which means it's exposed to external tampering. The signals traverse ultra-long reaches transparently only in the optical domain, which means that if there's an anomalous signal, it might not get interpreted or discarded. The physical infrastructure is extensively shared. It's used by multiple services with different protocols and different requirements, traversing multiple domains, over equipment by different vendors, and so on. And on top of all of this, the frequency, size, and sophistication of security breaches is increasing. Here are just a few examples of recorded occurrences of attacks on optical networks. For example, severing the cables in a cabinet, or tapping networks from telecom providers, police companies, and so on, as well as a series of attacks in the Bay Area where people dressed as maintenance personnel were going into manholes and cutting cables over a period of a year and a half. So when we talk about physical layer attacks, we typically divide them into two broad categories, depending on the goal of the attacker. The first one is eavesdropping, and here the attacker wants to gain unauthorized access to carried information. One of the ways of doing this is by abusing a well-known monitoring technique of creating temporary couplers, where a fiber is bent, which violates conditions of total internal reflection, and a part of the signal leaks out of the core. To protect from these attacks, we should rely on encryption techniques that can be performed at various network layers, including optical. The other broad category of attacks are service disruption attacks, where the goal of the attacker is to degrade or completely deny services. These attacks can be persistent or they can appear sporadically. They can be overt or covert. Their effects can be confined or can propagate through the network. And on top of the dependency on the exact attack technique, their consequences also depend on the way that the network is designed and how the resources are assigned to the services. In our work, we focus on service disruption attacks. When we talk about security management, we typically rely on three main pillars. They can also be viewed with respect of the timeline of an attack. Before anything happens in the network, we are concerned about security assurance. And to do that, we need to model the risk, assess the effects of different risk factors, and use this knowledge to minimize the exposure of the network to attacks. When an attack happens, we are concerned about attack cognition. To this end, we rely on collecting the data to get real-time insight into the network status and analyze this data to attribute different trends in performance to different types of breaches. And finally, after an attack, we are concerned with incident response to recover the affected services and adapt the network to make it less vulnerable for future occurrences of similar events. In our work, we are focusing primarily on attack cognition. The physical layer attacks that are known, that have been reported, are, for example, disabling critical components, where, for example, fibers are cut. Then inserting harmful signals. They can be in-band or out-of-band from the user connections. And external polarization scrambling, where the fiber is squeezed very quickly to cause rapid changes in polarization state that cannot be compensated by the coherent receiver. And in this work, we are focusing on the latter two because they are more challenging to detect. To understand the consequences of these attacks, we carried out experiments using the Telecom Italia's experimental testbed that is equipped with 6 reconfigurable add-drop multiplexers and coherent receivers commercially available. In this case, we are using Infinera's Groove G30 transponders. We subjected this testbed to attacks. They are generated by jamming the connections using a continuous wave laser or by squeezing the power driven by a sine wave generator. In the baseline scenario, when there are no attacks present, the spectrum looks like this. So we have 2 channels under test, and we have 4 loading channels to have realistic loading conditions. When out-of-band jamming is performed, we insert a harmful signal that is separated in spectrum from the 2 channels under test, and we then tune the power level of this signal to emulate a lighter and a stronger attack intensity. And we collect the data over a 24-hour observation time period. Every minute we collect 1 sample. In in-band jamming attacks, the spectrum of the jamming signal overlaps with one of the channels under test. Again, by changing the power level of this signal, we emulate a lighter and a stronger attack intensity, and again collect the data over a 24-hour window. When polarization scrambling is performed, we switch the sine wave generator on. We use different amplitude of the sine wave signal to emulate lighter and stronger attack intensity, and again collect the data over 24 hours. In the spectrum domain, we don't see any changes with respect to the baseline. Our attack monitoring framework looks like this. The coherent receivers report the OPM data to the monitoring and visualization server, which then communicates with the model for attack detection and identification based on machine learning, and another model for localizing the attack. It's also important to notice that we only use the health information from the destination where the signals need to be detected anyway. So we don't require any costly monitors or extra devices to be deployed in the network. We base the approach on processing the data provided by the coherent receivers, which is shown here. And every minute, the receivers provide the minimum, maximum, and average value of these features. Just to give you an insight into what the data set looks like, here we are showing the optical signal-to-noise ratio, the received optical power, and the bit error rate before forward error correction for the 2 channels under test. And what is visible from this set is that there are no clearly identifiable thresholds or even consistent trends in the data. And this is actually the main motivation why we chose to address this problem using machine learning. To diagnose security, we use different machine learning techniques. The first one is supervised learning, which relies on the a priori labeled data to train. Because of these labels, it's able to provide high granular diagnostic information. And this approach, this set of techniques is appropriate when we have complete information about what should be learned. On the other hand, unsupervised learning doesn't have the luxury of labeled data, so the main effort of the algorithm is to identify similarities between different inputs in order to cluster the data or extract features. Because of this, no highly granular diagnostic information can be provided, and it's mostly appropriate when we don't have a clear picture between mapping of the inputs and outputs or distinguishing between normal and abnormal conditions. And in semi-supervised learning, which is their hybrid, a small amount of data is labeled, and this helps the algorithm to facilitate detection of outliers. Also, it cannot provide high granular diagnostic information. And this approach is mostly appropriate when we cannot afford to label the majority of the data, or we simply cannot do it. And this is very appropriate for security scenarios where it's not very likely that we will have a complete representative data set with labels for all the possible attack scenarios that can occur. So to illustrate the implications of these different techniques to the life cycle of the network, where a new connection request arrives or a new attack type becomes known. So basically, the first step is to set up an optical channel and to validate that the performance satisfies the requirements. If supervised learning is used, then every time a new connection request comes or a new attack type appears, we need to acquire attack samples for each attack and each connection, and we need to use this labeled data for training. Semi-supervised learning uses only the normal operating conditions for training, while the unsupervised learning jumps straight to the operation and maintenance mode and does not have any training whatsoever. The challenge in security management is to address the false negatives and false positives, where the false negatives are more dangerous, speaking merely from a security point of view, because the undetected attacks can evolve to more disruptive events. And if we have a false positive, some countermeasures will be unnecessarily triggered, but there will be no major damage from the security point of view. When we use supervised learning for attack detection, we train it on previously acquired labeled experimental attack data, and this allows us to answer questions about the presence, the type, and the intensity of an attack. We implemented 8 different classifiers, and their accuracy is shown here. So we have artificial neural networks, support vector machines, Gaussian process, decision trees, random forests, naive Bayes, nearest neighbor, and quadratic discriminative analysis. The green columns show the average test accuracy for the case where half of the data set is used for training and half for testing. And then we further test the performance by using cross-validation technique, using k-folds, in our case k equals to 10, which means the data is divided into 10 subsets, and iteratively 9 of them are used for training while 1 is used for testing. The red diamonds show the average cross-validation accuracy, while the yellow blocks show the standard deviation of accuracy over the 10 folds. The confusion matrices of the worst and the best performing classifier are shown here. As we can see, neither one of them has any false positives or false negatives. And artificial neural networks perform very well. They only have a problem of misclassifying the intensity of the polarization scrambling attack in 1% of the cases. On the other hand, QDA has a problem with misclassifying attack types, and these two, in-band jamming and polarization scrambling, have different properties, which means that this is not acceptable performance. We also tested the relevance of features for the artificial neural networks. We started by having just one feature in the data set, the one that had the lowest classification error. And then we iteratively added one by one the feature that yielded the highest reduction in classification error. So what we can see here is that after adding 7 features, we have the same classification error performance as for the full data set. And this means that the complexity of the training phase could potentially be reduced, and this would allow more scalable adaptation to new attack types. We also tested the scalability of these classifiers, where we artificially generated 1 million samples, and we tested the execution time for each of them compared to the 1-minute threshold. Most of them are able to process that much data that quickly, and still leaving sufficient time for potential other actions within a monitoring cycle. When unsupervised learning is used to detect attacks, the main idea is to detect anomalies outside of the normal operation range. Here we use the density-based spatial clustering of applications with noise, or DB-scan, which doesn't have any prior knowledge of attacks. It's based on separating the monitoring samples into clusters and outliers. And this is done by tuning 2 key design parameters that determine the maximum distance between 2 samples for them to be considered neighbors, and the minimum number of neighbors for a sample to be considered a core sample. The only question that they can answer is whether there's an attack present or not. When semi-supervised learning is used, the logic is similar, detecting anomalies outside of the normal operation range, but this normal operation range is known, and the model is trained with the normal samples. Here we used one-class support vector machine, or OCSVM, which infers the properties of normal cases and distinguishes them from abnormal ones. As in DB-scan, it doesn't have prior knowledge of attacks and only can answer a question about the presence of an attack. The performance of these two approaches is shown here for different parameter settings in DB-scan and different kernels in OCSVM, which are quite scattered. The lines denote the Pareto frontiers, and as we can see here, the OCSVM performs better. It can achieve 5.3% of false negatives and 1.7% of false positives, whereas the DB-scan cannot perform that well. And the influence of these relatively bad performance results can be alleviated by an approach we call window-based attack detection. It's still under review, so I cannot give you the details here, but the idea is not to rely on the instantaneous response of the machine learning approaches, but instead to design the windows for attack detection and the thresholds on the number of attack samples that need to be detected before an alarm is raised. And the final step is localization of the attack source. So all the approaches before only give us an answer on the individual security status of connections, but we don't have an insight into where an attack was performed in the network. So the idea is to correlate these connection statuses provided by the machine learning approaches and use the network as an attack sensor. We can illustrate on a simple example similar to our example from before. So we can, for different attack types, and here we are using the attack types whose effects are confined to links, which are polarization scrambling and out-of-band jamming. And for each potential location, we can predetermine the set or subset of connections that will be degraded. These binary words are called attack syndromes, and in case they are unique, we don't need any extra diagnostic effort to localize the attack source. So, for example, if C1 and C2 are reported as degraded, then we can deduce that the location was link BF. However, of course, these words are not always unique, as is the case with these two and these four words. So we need to add monitoring probes to break these ambiguous syndromes. If we establish monitoring probe C3 on link FE, then we are effectively adding distinguishing bits to these two words. And then to break between these four words, we need to add 2 bits to each of them. And this is done by establishing C4 and C5 in this way. And adding distinguishing bit combinations. The mathematical framework behind establishing these probes in a way to minimize the number of necessary resources for them is presented in this paper. All of the code that I mentioned so far, of the approaches that I mentioned, is available online on GitHub, so feel free to check it out. And just to conclude, I would like to list some open network security challenges. One of them is related to enabling multi-layer security management and try to leverage on the exchange of information between the different layers instead of managing the security of each of them in a separate way. The second would be achieving situation awareness in complex network ecosystems so that the network is able to perceive its status, comprehend it, and project its future states. Developing autonomous self-defense strategy is definitely something that is necessary, as is the integration of all of these techniques with existing network control and management solutions. With this, I would like to conclude my talk and thank you for your attention. If you have any questions or would like to discuss anything, feel free to contact me. Thank you very much.